All right, hi Year 11s, this is Mr. Lim here again, and this is our last video on hydrocarbons, number 15, observations of reactions, number 2. So let's get started. All right, so we're going to be learning about colors of halogens in organic solvents now this time, and describing reactants and products, and then how the solubility of it works and how it affects its observations. So let's go. All right, so hydrocarbons reactions can sometimes be in the form of mixing two liquids. Okay, so in the previous video, we dealt with actually hydrocarbon in gaseous form, but hydrocarbons can also be in liquid form. And so when you mix a hydrocarbon in liquid form with a halogen in aqueous solution, something interesting happens. And let's go through what happens. When this occurs, two things can happen. A reaction can occur or a reaction won't occur. But both will have some visible change occur due to the nature of halogens and hydrocarbons. So a reaction can occur or a reaction won't occur, but in both cases, you're still going to see something happen, and you still will need to write about what happens to those things there, right? Regardless of a reaction occurring or not, because the halogen is going to move around when it's in there. So let's have a look at why. So halogens will preferentially dissolve into organic solvents, like hydrocarbons, rather than water. So when you add a chlorine water, which is generally, what color? Pale yellow. That means that the chlorine is dissolved in that water and it's causing it to be pale yellow. But as soon as you mix that chlorine water with a hydrocarbon, the chlorines are going to start moving into the organic phase, or the hydrocarbon phase, right? Which means that it's going to change something. Let's keep on reading on. As soon as you combine the two liquids, that's what we just said, halogen, which was dissolved in the water in the aqueous solution, will move to the liquid hydrocarbon, right, in this manner. So let's draw it out. See what happens. So here you have your water, your aqueous phase. All right, and here you have some chlorines. Okay, so those chlorines are sitting inside that, turning and making that pale yellow. Now you add your hydrocarbon phase in. Hydrocarbon phase in, right? And as soon as you do that, the chlorine is going to move from, whoops, come on. I only want the, nah. Those chlorines are going to move from the aqueous phase to the hydrocarbon phase, which means that, remember, when they're, whoops, don't want that, I want that one. When they're here, they make the water look yellow. So when they move to there, the water is going to change its color and no longer be yellow. So yellow, pale yellow, and then not yellow, right? So what that means is that the water will lose its color if the halogen creates a color in aqueous solution, all right? And then the hydrocarbon may change color due to the presence of the halogen in the hydrocarbon. So chlorine in organic solvent actually doesn't have a color, so that hydrocarbon is still going to be colorless even when the chlorine goes into it. But say I have something like, instead bromine. Okay, so that bromine in the aqueous solution, when it's, come here. You, one group. You, move by yourself. Okay, so when it's in this aqueous solution, it is orange. When it leaves this, it's going to lose, the aqueous phase is going to lose its orange color. So this is now colorless water. All right, so colorless aqueous solution. Now that the bromine has entered this hydrocarbon, you would have said it was colorless at the beginning, so it is colorless at the beginning, then the bromine moves into it, and it is going to now be, color of halogen in the organic solvent when it's Br is red. So it's going to go from colorless, now this part is colorless, and then it's going to go red as the bromine moves into it, right? So the hydrocarbon can change color due to the presence of the halogen in the hydrocarbon, right? This may be temporary if the hydrocarbon, it's over here, this may be temporary if the hydrocarbon reacts spontaneously with the halogen, or it might be permanent if the hydrocarbon doesn't react, right? So all you know for now is that you mix these two things together, the halogens start moving into the hydrocarbon phase, all right? And it can change the color of the the aqueous phase, which is the bottom phase, and the hydrocarbon phase, which is the top phase. It can change color if the halogen does that as it moves across. But now we have to think, what actually happens? Will a reaction occur? All right? So once the halogen has moved into the hydrocarbon, it can react or it might not react, right? So let's have a look, all right? So let's just say, here's our beaker. That's what I want. Here's our beaker again. Oops, that's too much water. Let's make the aqueous phase down here. Let's say, again, it is bromine water. Okay, so this is bromine water. Bromine water, which is what color? Orange. And then you add, let's say, some hexene, 1-hexene. Okay, so that 1-hexene is a liquid, right? This is going to be colorless. Okay, so what's going to happen? These bromines are going to, damn it. These bromines are going to move. These bromines are going to move into the colorless hexene, and then suddenly the hexene is going to change color to red. However, because it's a hexene, it's going to react with the Br2. And it's going to undergo an addition reaction, which means that these bromines are going to go. Okay, and by go, I mean like, actually react, but for now, I'm just going to put them over here. All right, so you're going to form C6H12Br2, being the 1,2-dibromo hexane, right? So it will form an alkyl halide, right? And that is a colorless substance, okay? So if it forms an alkyl halide, right, well, they'll be more soluble in the hydrocarbon and they'll stay there. Since the alkyl halides are colorless, you may see the hydrocarbon change color due to the halogen dissolving in it. So that's the idea of, okay, nope, ungroup. Come on. Ungroup. Okay. So remember, you have orange liquid added to colorless liquid. The orange liquid becomes colorless and the colorless liquid becomes red. Then those things that make it red immediately react and go away and form this, which is colorless. So it'll go red and then it will go colorless again, right? And that might even be so instantaneous that you may not even see it, right? But that's what's happening at the atomic level when you add those two things together, right? So that's what will happen. But let's just say that instead of adding it to 1-hexene, let's say that we added it to hexane. Okay, so hexane instead, which is a alkane, and we're going to do this in the absence of UV light. Absence of UV light. So what's going to happen? You drop these two together, the halogen's going to immediately move into the hydrocarbon phase, right? The water is going to go from orange to colorless, and then the colorless hexane is going to go red again, right? However, this reaction will not occur unless there's UV light. So this reaction will not occur until I open that lid. And so the Br2 stays there and makes that hexane red until, well, forever, until something changes, right? So that Br2 is going to stay there until something happens. So let's say I then suddenly take away the lid, right? And now I have UV light. So this Br2 is going to start to react, and like, I'm just going to put it over here to keep the idea there, all right? But it's going to react and form C6H13Br, the alkyl halide, and it's also going to form HBr, okay? So let's just make sure that those are separate things. Okay. So those are now separate things. So what happens is that if these two are, these are not separate. Come on, ungroup. Okay, so now these two things were made and they are separate things. And what's going to happen is that this alkyl halide is going to stay there because it is more soluble in the hydrocarbon. But the hydrogen halide, it will be more soluble in the water, and so it will go down into the water, right? But that hydrogen halide is colorless, and so therefore you're not going to see anything in it, but at least you know that that's where it is, all right? So that's the idea about what can happen when there's no UV light, when you have no substitution reaction. And then when you add the UV light, the substitution starts to occur, and you might see it change color from red to now colorless, because now it is no longer Br in there, it's now this C6H13Br. Okay, that's the idea there. But let's go back to this one here. In terms of it being in excess or not, so let's go say, get rid of that one there and get rid of that one there and bring these ones back. Okay, so let's just say that this is no longer the hexane, and let's go put it back into the 1-hexene. Okay, so now I say that there is excess bromine water. So when these things move into this thing here, maybe only these ones, okay, so remember, orange in here, so the bottom layer is orange, the top layer is colorless, it moves in, now the bottom layer is colorless and the top layer is red, right? Now we say that actually there's so much bromine in here that there's going to be some left. So this bromine goes away and turns into this stuff here, but there's still going to be some Br2 left because it was in excess. And if it was in excess, this entire layer, that layer there, is going to go from, well, red to less red. And it's going to be less red because there's still the presence of this here instead of colorless, where all of this goes away. Right? So you've just got to be aware of that stuff there. Okay? So that's that. See how you go, and we'll see if we can do these questions in class. All right, adios. So be aware of the substances, which substance is in excess and which one is limiting, as this will affect the color at the end of the reaction, especially if the halogen is in excess. Okay, so also be aware that the presence of UV light is going to make some stuff a difference, and that's what we talked about before.